Well, I told you guys that I had other ideas and versions I wanted to work on in that last video. I was busy. If you're looking to upgrade your PC cooling, check out the new Arctic P12 lineup. The P12 Pro is built for maximum radiator and heatsink performance with high static pressure and a redesigned blade that's efficient without getting loud. Building a clean showcase PC, then the reverse blade version keeps your airflow correct without showing the ugly side of the fan. And if you want the quietest system possible, the low noise model is tuned specifically for silent operation. Every P12 fan includes PWM control with 0 RPM mode, long-lasting fluid dynamic bearings, and PWM PST so you can daisy chain multiple fans together from a single motherboard header. Check them out using the link in the description below. So if you guys haven't seen the other video where I took you through my journey of learning how to model something in Fusion 360, how to program my CNC, how to understand the materials, go and check that video out. It's long, it's like 45 minutes, but I take you literally from nothing to a final product. So I had set out to make my own CPU block, and I started with some very basic designs. And I was disappointed with the result that I had with the previous block, which was actually this one and that one. This was V1 right here. And I was disappointed with this block because of two things. One, it didn't perform as well as I'd hoped. I had set out on this goal to compete with the Optimus, well, compete's a very strong word, but to use the Optimus block for the CPU in my 7950X as sort of my benchmark to see how close I could come to a very well-manufactured, very well-performing block. In fact, they don't make blocks anymore, I don't believe, but they basically advertised they had like NASA-grade accuracy and quality in their machining abilities. And that was very evident with the way the blocks were machined and coated and just absolutely insane. Like they even Cerakoted their stuff.
Water just bounces right off.
Which I'm being told I should do. But anyway, I digress. I had set this goal of being within 5 degrees Celsius delta of their average temperature under load with Ada64 running CPU stress tests with cache stress as well, because I wanted to really heat up the die, obviously. So I actually was 7.5 C away. I was like, dang, I was like 50% farther away than I wanted to be. And so I really kind of went back to the drawing board and was like, what did I do wrong? Now, I did change 2 major variables on V2, and I made some huge improvements. Actually, I have V2 and V2.2, and we'll explain why we're now in the dot versions here in a moment. This is the original jet plate that I used right here, and you can see and a cold plate, I should say, with the jet fins. The fins are very tall. They're very, very tall in there. And there is a lot of surface area, but there also is a lot of Z-axis height away from the heat source, which is touching this end of the cold plate. The cold plate's also about twice as thick as the other brands were measuring. And I thought thicker meant, hey man, more thermal mass. That's great, we can hold more heat. Yeah, if we're trying to absorb heat and hang on to it, but we're trying to transfer heat from one thing to another, and the cold plate and the jet fins are the conduit at which we're trying to move that heat. And so by having like 2.75 millimeters thick on that cold plate, I started doing some calculations and looking up the formulas. I forget the name of the formula, but the formula told me I was literally almost 3 times as thermally resistant than what the other block designs were, just with that thickness alone. And with the height of the fins right here, we were having more than likely a huge temperature delta between the hottest point and the coldest point at the top, which meant we were probably building up quite a thermal barrier. Now, thermal barriers are something that, this is a really neat analogy here that I saw, I think it was Mythbusters that showed this. If you wanna know what a thermal barrier is, your body is creating a thermal barrier right now. If you're sitting still, you don't feel the thermal barrier because it's formed everywhere where your skin is exposed to the air. The temperature of your body is much warmer versus your ambient temperature, which might be 25 or 30 degrees colder than that. So the body heat is heating up the air around you, and you've got this cushion now that's between your skin and the atmosphere. If you want to know what it now feels like to remove that barrier momentarily, just move your arms. You feel the air because that air has now displaced that barrier, and now the cold air can touch your skin and you feel it. The same thing happens with liquid and temperature differential. So the way you break up that barrier is you need turbulence. I set out to create the smoothest block I could. The smoother the block, the less turbulent the flow is, the more thermal barrier can actually build up. So I started really kind of doing some research on thermal barrier, which is what then led to a lot of the design changes that I made in V2. So this is actually the first new cold plate I made with the thermal barrier in mind. You'll see that the inside now is much more recessed than it was obviously here. I mean, look at that. You can see right there, it's full height on the fins. These fins, although the same exact count, there's 2 rows removed. You can see we have a full perimeter flow now, but they're also 50% less in terms of Z-axis height, in terms of their thickness, but then I moved it down 1.5 millimeters into the plate. So now my plate's only 1.25 millimeters thick. So now I've gotten the fins closer to the source of heat. Now, I did change 2 things in this design. Look, in the scientific process, you should change 1 variable at a time. That way you know what the result of that one change was. I was running out of material. So I ordered more material, but it won't be here I'm leaving for a few days and it won't be here till after that, and I wanted to make some progress here. So not only did I change the fact that we have the jet plate now, or the cold plate now thinner, and the fins closer to the heat, I also went with a center fire. So if you look at the tops right here, this is my cross flow, which went with this guy right here, which is where the coolant just goes in one side, flows across, comes out the other. And this actually would have probably performed fine with the thinner cold plate and the lower fins. It probably would have been a fairly decent improvement. But then the more I started looking at modern blocks, I was like, every single modern block from like reputable CPU block manufacturers have a accelerator plate, like a little piece of stainless steel that's like in between the material. And I really had to sit there and look at that and go, what is the true purpose of that? And the purpose of that is a couple of things. One, it's designed to increase the velocity of the fluid splashing directly down on the jet fins and the cold plate. 2, it's designed to increase turbulence because of that sudden 90-degree hit into the jet plate and then disperse out to the sides. See, mine was able to make the smooth turn, and I even chamfered the jets to make it smoother going through there, which meant that I was really smoothing out the flow and it was really reducing the efficiency and heat transfer because that thermal barrier was probably not as disrupted as it needed to be. So when I really started looking at block design and realizing that even the cheap blocks on Amazon were starting to include those jet plates that fire it straight down, I was like, well, couldn't I just mill one of those into here? But here's the problem with this, and this was a failed print. I ended up doing another one right there, as you can see. So I had to not only push the middle here down farther into the plate to now make contact with the top, I created a jet plate built into the center. So if you look in there, you can see how part of the hole is showing for the port, right? And then it's designed to kind of spill into this open area here and then waterfall down onto the jet plate. And I thought to myself, if every block that's using the stainless steel insert is shaped like this, why is there need for the stainless steel insert? And this was just another version of that one right there. It's just this one, it looks sanded because I had to get these heights just right. Like I need that to press against this so that the fluid can't flow on top of the fins. It has to be forced through the fins straight down. This was just my final, like, hey, I actually got the height correct. So this one here, this was too tall, so that wasn't touching. And then there's another one somewhere where it was bottoming out on the jet plate before the O-ring could seal. So I had to make some changes to the cold plate as well on this version, which I'll take apart in a second and show you. You can see this one here has the wider, like D-shaped channel, and then this one has the skinny channel. These are actually 2 different versions I was trying. So on the charts we'll look at in a second, this is what's V2, right? So it's running basically this base plate, and it's running this center channel, which is only measuring 2 millimeters or 2.5 millimeters wide. And then this one here has the actual stainless steel insert. So this is V2.2 and this is V2, and they're running the same base plate. There's just 2 of them, so I could kind of switch them faster. I digress. Going back to what I was explaining about why the steel insert is there. that steel insert is designed to, like I said, increase that velocity through the top of the block into the jet plate and the microfins, which macrofins in my case, and then bounce really hard and go sideways with such turbulent force that it's breaking up any thermal barrier that can exist there. But the only way it can truly do that and even out that force is you need a larger volume above that opening than what you can get by simply milling it like this, because the only opening into this, and we'll show you here in the 3D model, is what is part of that port that is intersecting through that side wall. So then it's probably getting a higher velocity in the very center, but then the sides are weak because it's gonna wanna go straight down through. Back pressure will fill in some of that and then it'll trickle through the side, but that plate also increases the velocity and the evenness of the waterfall effect that's coming down onto the jet plate. So if we look at the chart here, you can see this is the same chart we had in the other video, where this is how V1 compared to the Optimus block. It was 7.5 C warmer at 81.5 C average. I was disappointed with that result. Most people were telling me, dude, if you came under 10 C difference for your first attempt while learning the process between a block that was like $300 versus yours with a hobby mill, you're doing pretty damn good. I was like, yeah, but I really set to do a 5C delta or less. So V2, as you can see now, the complication here was the multiple heights. So you can see how V1 just has 2 different Z-axis heights. V2 has 3 different axis heights, or Z-axis heights. So that complicated the design quite a bit here. But when I tested V2, before I charted the data and I was just kind of watching it on screen, I noticed right away when V1 went under load, it immediately went up to like 80C, 81C, bouncing up 79, 81, 85, 81. It was all kind of over the place, but it started off significantly higher than the Optimus block. V2, on the other hand, went to about 77 and then started bouncing around between like 77 and 81. So the average temp of the Optimus block was 74C. The average temp of V1 was 81.5, right? So we got that 7.5C delta. The differential between V2 was 79.5. So I dropped 2C by simply pushing the fins down and then doing the center channel thing. I cannot say which one led to the best improvement because I changed 2 variables at the same time. So I can say the combined difference, obviously, between these 2 variable shifts is 2C. And I'm like, all right, I'm now within 0.5 C of where I wanted to be, right? Because now I'm like, shit, I want to be within 5, and I'm at 5.5 away, 74 average versus 79.5. So then I went, well, how much does that jet plate insert really matter? And this is where like this design now technically has a little asterisk next to it because I had to steal one from another block. These are made out of stainless steel and they're usually laser cut. I do not have a way to laser cut anything. I do not have a laser cutter, nor do I have access to 304 stainless steel in 0.78 millimeter thickness, which is exactly what these are. So I stole this from a really old block, a really old EK Supremacy block, and their designs have progressed well past this as well. There it is. So now we have 4 Z-axis heights that I had to deal with because now I had to deal with the recess in there. I had to deal with the recess in there to make sure now this is not sticking out and now not causing it to bottom out. And another thing I did, and one of the reasons why I also remilled the bottom here, is I made my O-ring channel a little less deep. That way more of the O-ring sticks out the top, which gave me a better seal if some of those heights weren't perfect. So what I was dealing with was this guy, which worked just fine with this. This wasn't sealing with this. And that's because of the fact that you'll notice here, I have the O-ring channel, like this is only 0.15 millimeter, so it's 150 micron deep. The depth of this O-ring channel was just too much that when I put that index O-ring back in there, so it can only go one way, it wasn't sealing anymore. But I really wanted that index O-ring in there now because now it matters more than ever. But it took me about 3 attempts to get this measured properly, get that depth set right, get all 4 of those axes correct and still seal. and come up with V2.2. So like I say, it's got a little asterisk because I had to steal this. Looks like a razor blade. Don't think I didn't think about trying to use a razor blade and see if I could mill it, by the way, but stainless steel milling with the Macara Carvera with 304 stainlesses in my bits was not gonna end well. So I just had to steal this, and I'm not about to go buy a laser cutter to start cutting sheets of stainless so I can do inserts on a product I'm never gonna sell. So now if we look at the chart to see how V2.2 compares to the Optimus block and everything along the way, I dropped the average temp down to 76.7 C. 2.7 C delta from the Optimus block. As a nobody YouTuber who learned how to do this on his own and just was observing what other people are doing. Now, one thing I'm noticing here is you'll see there's a slight bow now in this bracket because of how many times I've mounted it down. I'm starting to wonder if that bow might be causing me some lift in the center of the block, because I did notice on this version, the paste didn't look quite as spread out as it did on the previous versions. One way I could test that is, although this is the pretty side, I could just simply flip it and mount it again. So now with that, now it being concave, going into convex, I could see now if the mounting pressure comes back. That's because of the fact that I'm just using aluminum as the bracket right here. The hold down bracket is somewhat of a, not complicated part, but you can see right here, right? It's not flat anymore. So anyway, I'm gonna have to probably go back to the drawing board on how I'm gonna deal with this. But if this is starting to bow and it's in between the block, right, like that, and it's bowing up, it could actually be lifting the block slightly off. So I might even have better temps that I'm not aware of. But I saw it shoot to 75 at the start of the test and then start climbing into the like 77, 79, 76, 77, 79. Now you notice looking at the chart, it's got a bit more range to it. Not entirely sure what that's all about, honestly. If you look at the Optimus block, there's no denying it's much more steady and stable, but this now is the kind of block that I could absolutely run every single day on any CPU and know that in everyday use case, gaming, light rendering, light editing, even regular editing, it will be absolutely fine. It would run all day long and be a great performing block. So I'm pretty excited with the results. And I feel like I can take a little bit of a break now because I've been waking up in the middle of the night, like seeing CAD in my head and measurements and flow design and like Hangover when he's seeing all the numbers and he's doing the card counting. It's like that. And my wife also said the other day I woke up in the middle of the night just going, fuck, it didn't work. My brain needs a break from this, but I'm really having a lot of fun with this because I want to step it up now. I want to water cool things maybe that aren't normally water cooled, like the steam machine, or maybe stuff other people have done, like the water cooling consoles, water cooling a laptop, just water cool all the things. I'm gonna start water cooling Phil if I've gotta, because of the fact that I'm just like, I need to now make my money back on this stuff, but it allows me to continue to learn and teach myself new things, which is why this entire project has been so much fun. Now, yes, this is a very standard design. There's nothing super crazy about it, but now that I understand the basic physics of thermal barriers, flow, resistance of material, right, all of that science, now I can start to try and fine tune. Because here's the thing, I had to play catch up for what these companies have learned over the last 20 years in 3 weeks, a little 3.5 weeks or whatever it's been. I think I caught up pretty quick. Now I ain't winning the race, but I'm still in the race, which is fun. And like I said, to be a dumb YouTuber talking about tech, I feel like I've come a long way and I'm excited about this. After I did V1, then I started watching YouTube videos of other channels that have attempted to build CPU blocks. Some of Linus's really early attempts before he got the big, crazy liquid, cooled and the big professional CNC machines where now you can just cut through anything. I think my first attempt went really, really well versus what everyone else was doing 5-7 years ago. 2.7 C, man. Like, I could just feel like I have a huge success already, but I know there's more room to be made up. I've got 0.6 millimeter carbide bits coming, so I can at least get these even finer, because the reason why we want it to be fine is the fact that we can have more surface area being touched by the fluid, which is now how we're going to increase the efficiency. All right, guys, thanks for watching. We'll take a little break from the CPU water block content. Some of you have asked, like, are you gonna try and make a GPU block? If you want to talk about scary because of all of the different crazy heights that are involved, I could probably go online and find the CAD drawings. All the water block manufacturer companies for GPUs, they get sent CAD of the card. Like it's a 3D model of the card, so they can know what all those heights are. I would have to be manually doing that. I feel like there's gotta be a card around here somewhere that I could potentially like, okay, if something bad happens to this, I won't feel terrible, but it would be a fun learning process along the way. We're also talking direct die, so contact pressure is important without being too much contact pressure. Maybe I'll do it. If enough of you commit to watching that series, I'll commit to trying on maybe something like a 3070 maybe? I don't know. Like, times are tough right now when it comes to tech and prices. I don't exactly want to just blow something up for the hell of it.
I liked your motherboard monoblock idea too. You were talking about that in the last video.
I guess that would be the natural progression, to go from CPU block to a monoblock, which is now dealing with a few different z-axis heights and capacitors and chokes to clear, then to GPU block where it's smaller. Now we're talking memory chips, we're talking VRMs, we're talking MOSFETs, you know, we're talking obviously the die, we're talking backplate, all that sort of stuff. So, all right guys, thanks for watching. It's been fun, but it's time to move on to something else. We'll see you in the next one.